Hello, welcome to my talk on Bernoulli's equations for potential flows, including both incompressible and compressible flows. In this talk, we will see the Bernoulli's equations can be derived based on the assumptions of an irrotational flow and of the inviscid flows. Thus, the Euler equation. Generally, when the flow velocity is small, for example, the Mach number is less than 0.3, the flow can be considered as incompressible. However, potential flows can be also valid for compressible flows, as in the subsonic flows, when the Mach number is between 0.3 and 0.8, and in the supersonic flows, when the flow Mach number is between 1.2 and 5.0. Thus, we will show the Bernoulli's equations for the compressible flows under the assumption of an ideal gas for the air. This is generally accepted for engineering applications. In addition, a more useful relation would be derived for the flow past the thin airfoils in small angles of attack. Thus, the famous Prandtl-Glauert compressibility collection can be derived. Before the derivation of the Bernoulli's equation for potential flows, we would like to see the conventional Bernoulli's equation first, which can be derived directly from Euler equation under the following assumptions. The flow is inviscid, therefore the governing equation is the Euler equation. The flow is steady, so the partial differentiation of the velocity vector with regard to time t is 0. The flow is incompressible, thus the fluid density ρ is constant. However, compressible flows are also possible, for instance, for an ideal gas, and a similar derivation would be presented in this talk. The body force must be conservative. The fluid gravitational force is such a conservative force, can be expressed in this form. That means the fluid gravitational force can be expressed as the gradient of a function, like here gz. And the flow is on the same streamline, such as the streamline in the fluid pipe in this drawing. Under the assumptions above, the conventional Bernoulli's equation can be derived, given as here. Vector v is the velocity vector, p is the pressure, and ρ is the density of the fluid. G is the gravitational acceleration, and C here is the integral constant. So if we apply the Bernoulli's equation for the pipe flow here, we can write the Bernoulli's equation as this. Here, the subscript 1 means the parameters at the section A1, and the subscript 2 means the parameters at the section A2. So using this Bernoulli's equation, we can build the relation between the pressure and the fluid velocity, as well as the height of the pipe. Like the conventional Bernoulli's equation for some flows, where the flow velocity can be obtained easily. For instance, for the paper flow, if the flow rate is known. But for the complete flow dynamics, we might need to employ the Bernoulli's equation to link the fluid velocity and the fluid pressure so that the force, moment, and the fluid power, etc. can be calculated. Similarly, in the very useful potential flow, for instance, the flows past an airfoil or a wing, we can simply solve the velocity potential from the simple Laplace equation for the incompressible flows. And this can be done by the applications of the simple kinematic boundary conditions. For instance, the no penetration condition given as this on the body surface, and the calculation of the flow velocity vector and the three velocity components in the Cartesian coordinates given as this. Now we can see if we are only interested in the fluid velocity, then we do have the solution as we expect. And it is interesting to note that we do not apply the fluid dynamic equation, the Navier-Stokes equation, or Euler equation. However, for most practical problems, we might be more interested in the force and the moment acting on the structure by the fluid, such as the lift acting on the airfoil and or wings. Thus, we must calculate the fluid pressure on the structure surface. This can be done using the Bernoulli's equation. Here, the Bernoulli's equation for potential flows. When the fluid speed is not very high, for instance, the fluid Mach number m is less than 0.3, the flow can be regarded as incompressible. Here, we will examine the incompressible potential flow first. Similarly to the conventional Bernoulli's equation, the derivation would be based on Euler equation, the governing equation for the fluid motion in inviscid flow. However, we will see there will be some difference between the conventional Bernoulli's equation and the Bernoulli's equation for the potential flows. The Euler equation is given as this. Here, we can see the body force is the fluid gravitational force, as we see for most potential flow problems. And we will see the gravitational force is a conservative force. For the potential flows, the velocity vector can be given simply as this, as the gradient, the velocity potential function phi. So to examine the convective acceleration given here, we can use the velocity calculus identity. The expression would be given as this for vector A and B. Now, if we take both vector A and B as the velocity vector V, and then we have the expression as this. As we know, for the potential flow, the core of the velocity vector would be 0. Therefore, we have the convective acceleration term given as this. And if we apply the velocity potential function, we have this. As such, the Euler equation can be expressed as the form as this. And here, we can see the body force is conservative. If we see this mathematical expression, the body force can be expressed as the gradient of a function, gz here. Thus, the body force is a conservative force. And here we can see we exchange the order of the operation, the Laplace and the partial differentiation given as this. So from the expression for the potential flow, we can see this differential equation is integrable. So we can integrate this equation as this. This is the Bernoulli equation. And we can see this is the integral form of this equation. This is why we called the Bernoulli's equation is the integral form of the Euler equation. And we can write the equation as this. We can see the velocity expression as here. We write the Bernoulli's equation for the incompressible potential flow as this because we want to compare to the conventional Bernoulli's equation. So if we compare these two Bernoulli's equation, we can see there is an unsteady term for the Bernoulli's equation for incompressible potential flow. So here we can see there are some requirements for the Bernoulli's equation for the incompressible potential flow. The flow is inviscid and incompressible. The body force must be conservative. Here, the conservative gravitational force is only included. And the flow is irrotational, but can be both steady and unsteady. Now, in this slide, I will show how we can calculate the pressure coefficient if the velocity is calculated using the potential flow theory. And from the previous derivation, we can see the four Bernoulli's equation for incompressible potential flow is given as this. Now we take the NACA 4412 as an example. Suppose we have solved the flow field as shown in this plot. We have the velocity for 3 points. First of all, this question is a steady problem, so the first term would be 0. As such, the Bernoulli's equation for this application would be given as this. Here, the expression on the left-hand side is the dynamic pressure term plus the static pressure at the far field. Use the subscript infinite. And the right-hand side term is for the field point, any point in the field. Here, we use the subscript I equaling to 0, 1, and 2. So we can calculate the pressure difference given as this. And based on the convention, the pressure coefficient Cp is defined as this expression, the pressure difference divided by the dynamic pressure at the far field, given as this. And here, the subscript I can be 0, 1, 2, and for other field points as well. So for incompressible flow, the density at the field point, rho, would be same as the density at the far field, rho infinite. So we can obtain the pressure coefficient given as this expression. So as such, we can see, as in this definition, the maximum pressure coefficient would be 1 because the second term on the right-hand side would be equal or larger than 0. So the maximum pressure coefficient happens at the field velocity is 0. That means at the stagnant point. So if we look at the pressure coefficient in this plot, we can see Cp0 is 1, and Cp1 is very close to 0, and Cp2 is about minus 0.8. So all these points are for the pressure coefficient on the upper surface and this on the lower surface. The next few slides, we will consider the Bernoulli's equation for the compressible potential flow. As we have shown before, the potential flow theory can be varied for the supersonic flows for the Mach number between 0.3 and 0.8, and for the supersonic flows of the Mach number 1.2 to 5.0. And again, the derivation for the Bernoulli's equation starts from the Euler equation, and the similar methodology we used as for the incompressible potential flow. So the Euler equation can be expressed as in this. The only difference here with the expression for the incompressible potential flow is for the density. Now, for the compressible flow, the density ρ is not a constant. So we can't write this equation simply as the interglobal equation as we have obtained for the incompressible potential flow. To obtain the Bernoulli's equation for the compressible potential flows, the important thing is we need to get this term interglobal. So for engineering applications, we consider the air as an ideal gas, and under an isentropic process, which is a reversible adiabatic process. So the relation between the air pressure and the air density is given as this. And here, gamma is the specific heat ratio. For the air, gamma is 1.4. Or we can express a relation as this, use the parameters for the undisturbed incoming flow, the parameters at the far field, P infinite or rho infinite. So we can obtain rho would be given as in this expression. We substitute this density into the equation here. We have the expression as this. Now this term is only dependent on pressure. It is integrable. So we can integrate this equation. We obtain the integral form of the Euler equation for the compressible potential flow as this. And we can make mathematical manipulation. We can obtain the Bernoulli's equation for the compressible potential flow as this. If we compare the Bernoulli's equation for the compressible potential flow to the Bernoulli's equation for the incompressible potential flow, we can see only for the pressure term is different. So if gamma is much larger than 1, then the Bernoulli's equation for the compressible potential flow would be same as the Bernoulli's equation for the incompressible potential flow. Now here, the more useful relation for the compressible potential flow is the linearized expressions for the compressible flow past the thin airfoil. For such a case, we can build the simple relation between the air pressure and the velocity in terms of pressure coefficient Cp. See this drawing. The high-speed flow U infinite past the thin airfoil. When the angle of attack for the airfoil is small, so the flow past the airfoil would be disturbed slightly. Based on the convention, the pressure coefficient is calculated as this. The dynamic pressure for the undisturbed incoming flow is defined as this. And if we use the speed of sound at the far field, A infinite calculated as this equation. So we can write the dynamic pressure for the undisturbed incoming flow as in this form. Here, m infinite is the Mach number for the undisturbed incoming flow. So we put this dynamic equation into the pressure coefficient. We can obtain the expression for the pressure coefficient given as this. Same as the assumptions for deriving the Bernoulli's equation for the compressible flow. Here, the air is considered as an ideal gas, and under an isentropic process, we have the relation between the pressure and the temperature given in this equation. And following the reference, the book Fundamentals of Aerodynamics, we can obtain the relation between the temperature and the velocity component given in this form. So here we take 2D for simplification. So if we take this expression into the relation between the pressure and the temperature, we can obtain the expression as this. And consider the second term in the bracket is much smaller than the unit, so we can have the approximation for the pressure expression given as this and this. Based on the derivation in the previous slides, Cp and the relation of the pressure and the velocity component. So we can obtain the pressure coefficient given as this, and consider the higher order term of the disturbance velocity component. The first term on the right-hand side is much larger than the second term. Therefore, we have the approximation for the pressure coefficient Cp given as this. So in here, we consider the compressible subsonic flow. The linearized equation for the velocity potential is given as this, with the compressibility scale factor beta given as this. So following the reference, the same book, Fundamentals of Aerodynamics, if we perform the transformation as the following for this coordinate transformation and the velocity potential transformation, and under this transformations, the transformed boundary condition would be same as those for the compressible flows. If you like, you can find more details in the reference book. So perform the mathematical derivation, we can obtain the equation for the transformed velocity potential phi bar given as this. So this is the Laplace equation. That means phi bar is equivalent to the potential in an incompressible flow. So solving the transformed potential equation, we can obtain the pressure coefficient given as this, Cp0. This pressure coefficient corresponds to the case of incompressible flow. So once we solve the Laplace equation for the transformed potential function, we can calculate the pressure coefficient Cp0. And again, following the reference, the pressure coefficient for the compressible flow is given as Cp equaling this, and U is calculated as the partial differentiation of the velocity potential function with regard to x. And consider the coordinate transform and the velocity potential function transform. We can obtain the expression as this and this. Therefore, the pressure coefficient in compressible flow would be given as this and in this. So, we obtain the famous Prandtl-Glauert compressibility collection.